este tipo de materias. Muchas gracias por estar aquí. Dentro del programa de actividades que tenemos, bueno, el día de mañana vamos a tener Quasars and Large Scale Structures, también por Gerard Williger, que es nuestro invitado del día de hoy. Y en la tarde, de 6 a 8, vamos a tener astrofísica de un planeta habitado, que lo va a dar Alejandro Márquez Lugo, otro compañero de la astronomía. Y si las condiciones climatológicas lo permiten, mañana también tendremos observación nocturna, acabando la conferencia a las 8. Todo depende pues de cómo esté la cuestión climática. El jueves vamos a tener choques de vientos estelares. Viene Joel Sánchez Bermúdez de la UNAM y nos va a platicar de cómo se están viendo estas atmósferas estelares, la interacción gracias al James Webb. Y su servidor va a estar aquí de 6 a 8 de la noche, hablando de la supernova de Kepler y la estrella de Belén, de la astronomía china, los evangelios apócrifos, cómo estas estrellas que han explotado, que se han visto, han cambiado pues el curso, la modelaje de muchas estructuras cosmológicas, creencias, etcétera, etcétera. ¿No? Esa es la historia al respecto. Mariana, muchas gracias, te agradezco mucho. Y tenemos por último el viernes, terminamos esta semana de la astronomía y las conferencias con habitabilidad en sistemas planetarios, buscando vida en otros planetas, de Leticia Carigui, una compañera de la UNAM, astrofísica, también con este tema que es muy de boga, está muy en auge esto de los exoplanetas, planetas en otras estrellas y esto de la habitabilidad. Además de esto, tenemos actividades en biblioteca. Sí, tenemos un taller de realidad virtual y aumentada en el edificio J, en mis compañeras, no sé si andan por aquí, ¿no? Natalia, por favor, muy bien, ella está junto con César Lozano, encargada de este montaje de la experiencia de realidad virtual. Aquí, muy bien, a ver, levanten la mano para que las conozcan, muchas gracias. También están nuestras compañeras de observación solar, levante la mano nuestros compañeros de observación solar, ¿no están? Ahí están, muy bien. También afuera del edificio J, si ustedes gustan observar el sol, tenemos 2 telescopios con filtro, entonces para que vean las manchas, las protuberancias, todo esto, ahí estamos a sus órdenes. ¿A qué horas están? A ver, platíquenles, por favor. ¿Y quién nos puede platicar mañana de lo de la observación nocturna? ¿Quién está en esto de la observación nocturna? A ver, compañero, adelante, platícanos. Gracias.
Sí, en el edificio F, observación de cielo nocturno, de 8 a 10 de la noche, para que pasen ahí.
Ojalá y nos acompañen. Además, vamos a tener de nuevo a Chris Greeny, allí en biblioteca. Nos va a hablar de 2 temas muy interesantes: Jesuits Astronomers, The New Telescope and the Moon, y también Jesuits Astronomers, The New Telescope and Jupiter. Ambas van a ser mañana miércoles y el jueves en el Ágora de Biblioteca a las 4 de la tarde. Y Jerry va a estar de nuevo en biblioteca. Mañana va a tener otra conferencia aquí, y en biblioteca va a estar también él hablándonos de The Great North American Eclipse, de 11 a 12 también ahí en el Ágora, ¿de acuerdo? Entonces hay varias actividades, ojalá y nos visiten, ¿no? Aprovechen esta semana de la astronomía. Cambridge, allá en el Reino Unido. Él también estudió su Bachelor in Science, su carrera en Astronomy, Mathematics and Physics. Es un triple major, tres áreas mayores, ¿verdad? Ahí en el Ohio State University. Bueno, tiene un currículum muy amplio. Voy a simplemente decir algunas cosas importantes de Jerry y él ya se presentará, verá qué les cuenta o qué no les cuenta, ¿verdad? Ha sido investigador, profesor visitante, tanto en Chile, en los observatorios del sur europeos, ¿verdad? Ha sido profesor en Francia, en la Universidad de Louisville, ha estado, bueno, en varios trabajos de investigación, como es muy extenso su trabajo, en trabajos de postdoctorado. Pertenece a la American Astronomical Society, the European Astronomical Society, the Royal Astronomical Society, en fin. Entonces, es una persona muy interesante para que ustedes, bueno, cuando quieran hablar de temas, va a hablar de 3 temas diferentes en esta Semana de Astronomía, pues pueden dialogar con él terminando. Un aplauso para Jerry, muchas gracias a todos ustedes. Es importante que hablemos por el micrófono porque está siendo transmitida y grabada la sesión.
Okay. Primero, antes de todo, inglés es mi idioma materna. Wow. Maybe my computer is from Vulcan. It has green blood. That might be nice. Cuidado. Okay. Yours or mine? You don't need these. Gracias por la paciencia. Great. Okay. Otro caballo. All right. So, rule for giving talks is tell people what you're going to say it, and then tell them what you said. So, first of all, I'm going to tell you where do elements come from. I'm sure that all of you learned this at your mother's knees when you were very young, but it's good to have a review. How do we go from elements to molecules? Where do the molecules live? Giant clouds. And then molecules closer to home in the solar system. So they start out in places like this, and then they end up in places like this. They make things like this. Eventually, things like that. So, where do little elements come from? How many of you have seen a television show, a documentary of scientists called Big Bang Theory? I hope. Okay, if you have not seen it, it's your homework, tarea. Watch Big Bang Theory. The beginning is correct in the time scale. The whole universe was a hot, dense place. After that, they take a little license. And actually, in the first few minutes of the universe, all of the elements that were made for a long time after that were formed. That would be hydrogen, helium, a little bit of lithium. And hydrogen came in 2 stable forms, hydrogen deuterium, a little bit of tritium, and helium came in 2 forms as well, the form of helium with 1 neutron, helium with 2 neutrons, which was much more common. And so what happened in the Big Bang was we had protons and neutrons flying around. Sometimes the protons and the neutrons would stick together from what's called a strong nuclear force. Another neutron might come along and eventually make helium. Video here. Nice animation. I always believe in visual effects. So, what? Oh, whoa, 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 why does this not? a trick. I'm trying to remember what it was. Oh, I think I know what it is. Oh, we don't have videos, and that will be very boring. There. This again. That. I've embedded a number of little videos. Oh, this would be sad. Okay. Since this is a Windows machine, I don't know how to do it, but I will leave the power. Yeah. Why doesn't this appear? It's not my computer. Probably okay. Yes. The videos. Disculpas por la pausa técnica. Hooray! Okay. Okay. I'll restart. All right. So what we have here is we have protons and neutrons flying around, and some of them stick together and make heavy hydrogen and helium. And eventually, actually, they'll also capture electrons. So this is what happened in the first few minutes of the universe when the temperature was like in the middle of a giant star. Okay, enough of that. Let's go back to the slideshow, please. I appreciate your helping, by the way. All right. Okay, so that's how we made elements. Now, in the middle of a star, this is happening all the time. Stars are big balls of gas. The universe is about 90% hydrogen by number, and about 9% helium. The beginning was 10% helium, something like that. And so, in the middle of a star, there's a balance between gravity and pressure. And what happens is the gravity compresses the material so much it heats up to the point where the protons will slam into each other. You need a minimum of about 6 million Kelvin to do it, and that will make helium through several steps. And so this is how stars shine stably for billions of years. And they convert hydrogen to helium smoothly, stably, and they give off light and heat, and everything is very nice. There comes a point where the hydrogen is mostly converted into helium. And then what happens is you have a core of helium, and to fuse helium, it takes 100 million Kelvin, not 6 million Kelvin. The temperature is not hot enough. So the helium just sits there. On the other end, so the balance gravity goes off. Pressure comes from the fusion, turning hydrogen into helium, and giving off heat and light. And so what happens is a star will start to compress a little bit, and then a shell around the core will get hot enough to fuse the hydrogen in the shell. And so you start fusion in a shell a little bit closer to the surface of the star, and then that actually causes the gas to expand and cool and become red, because red is the color of cool things, and yellow and blue are the colors of hotter things, and you get a giant red star. It's called a red giant. Now, this can happen for a while. The sun can fuse hydrogen for 10 billion years, depending on the size of a star. Actually, the bigger stars fuse hydrogen for shorter times because they fuse very, very fast. It's like having the difference between a sports car, which burns a lot of gasoline fast, or an economy car, which is very efficient with fuel. Our sun is a middle-sized star, so it's a middle efficiency star, but the big, massive stars actually burn through their hydrogen much faster. So you have this shell of hydrogen burning around the core. That can happen for a short time, but even that will run out, and eventually the gravity will win, because gravity always wins. It'll compress the core until it gets to 100 million Kelvin, and then it will start to convert helium into carbon, because 3 helium atoms will make a carbon, and that can happen for anywhere from 100 million to 1 billion years, in what's called a red giant. Now, when the red giant is doing this expanding and contracting, it will emit some of its outer shell or puff it off. It's not an explosion. Think of a dandelion. Are there dandelions here? Oh, okay. And they have seeds which are very loosely attached, and you can blow them with a little wind or a little breath, and it will fly off. That's what the outer parts of a red giant are like. Now, there is also convection happening in the star. So the carbon in the middle will get moved to the surface of the star, and the hydrogen in the surface will get moved to the middle, and then carbon will fly out in this gas. This is carbon-rich gas. Now, carbon sticks together very, very well, and it takes a high temperature to force it apart. So the carbon naturally will stick together to make what we call dust grains. Now, it's not like dust in the dirt. These dust grains are very fine, like smoke particles, but they still may be many thousands or 1 million atoms. So you can think of red giant stars as polluting what's called the interstellar medium with carbon, just like big trucks like this one. This is the terrestrial equivalent of a red giant star. Now, you may say you don't like following that. Well, that's true. If you have to breathe it, that's pretty awful. On the other hand, the carbon that comes out of these stars is very important, because the carbon in these stars formed us. So here's a picture of a cloud of gas from a former red giant star. There's a star in the middle here, which astronomers sometimes have bad imaginations for names. It's called the central star of a planetary nebula. This is called a planetary nebula because in the early telescopes it was round and it looked like a planet. But it's not a planet because it doesn't move and it's much farther away than the planets. So it has this shell of gas. It looks like a ring because we're looking at it through, basically through a silhouette, or we're looking at it edge on. And if we take a look with the Hubble Space Telescope, we can see gas coming out of this star in all directions, passing lumps of dust. It's just like pebbles or rocks in a river. So what you get in a red giant star eventually, because this process will continue, it will fuse helium into carbon and then run out. And then the carbon will sit there, and carbon takes a higher temperature to fuse together, and then the star will start to compress from gravity, and then it will start to fuse carbon into oxygen, and then oxygen into neon. You're adding helium atoms every time, so the atomic number goes up by 2. And what you end up with is a star with shells like an onion, with the heaviest elements in the middle and the lighter ones outside, from all of these shells of fusion and the core of fusion, until you get to iron. Now, if you put together 3 helium atoms into carbon, put them together and make carbon, you'll get some energy. If you add a helium to carbon and make oxygen, you'll get some energy. You add some helium to oxygen, you'll get neon, you get energy. But every time you move to a higher element, you get less and less energy. When you get to iron, it's 0. You can't make an element heavier than iron by putting something together and getting energy out of it. It won't work. But the energy that you get out of it is what holds up the star against its own gravity. So eventually what happens is you get a core of iron, and it just sits there, and it's not going to fuse anymore. And eventually these shells actually, for these higher elements, the shell burning, the shell fusion, will happen in shorter times, because there are fewer and fewer of these heavy atoms. You start out with a lot of hydrogen atoms, and you have a few iron atoms. So you can take a few days to fuse, say, silicon or magnesium or something like that. And eventually, gravity wins. And there's not enough heat and pressure to hold up the star against its own gravity, and the gravity will start to crunch it in. But now there's no fusion. What's going to happen? The iron atoms start to fall apart, actually. And they turn back into helium atoms, and then a bunch of neutrinos come out, and energy comes out. And then what happens is the protons eventually get fused into electrons here, and a ball of neutron forms. Now, a ball of neutrons is very, very hard. And so the star is collapsing, and this takes a second maybe, and it meets this hard ball of neutrons and bounces. And as it bounces back, this shock wave forms. The material's traveling faster than the speed of sound, and a whole bunch of other fusion happens. That's what's called endothermic. So you can make elements heavier than iron as long as you put energy in. You'll get less energy out. And that's what happens in basically an explosion called a supernova. And what's left is a ball of neutrons. And it's called a core collapse supernova. And what it does is it scatters all of these heavy elements out into space at thousands of kilometers per second, and it expands in a big cloud, and it will expand for thousands of years into the space between the stars. What happens to the ball of neutrons? It's rotating very fast, it has strong magnetic fields, and it gives off radio waves. It's spinning maybe up to 1,000 times a second, and so it acts like a lighthouse in space. So, after several generations of these supernovae, instead of having hydrogen, helium, and a little bit of lithium, what we have is hydrogen, helium, yes, this is by weight, not by mass, not by numbers anymore. So by mass, the universe is about 74% hydrogen, about 24% helium, about 1% oxygen, 0.5% carbon, and then all of these other heavier elements, even less. Or if you want a pie chart, this is what the universe is made of after 13 billion years of stars making heavy elements. We have all of these heavy elements making up this tiny amount by mass of the universe. But they're important because they make us. So there's another way to look at how elements are made. Here's a periodic table. And what was made in the Big Bang is these blue elements, hydrogen, helium, a teeny tiny bit of lithium. Exploding massive stars, which was what I described, makes these middle level elements, so up to iron and then even up to, say, selenium and bromine, krypton, so on. There are some exploding white dwarfs, which is another way to have stars explode, and they make also some of these middle range elements. And then there are neutron stars, which I just described. Neutron stars are what's left here, and they can form in pairs, and when they merge, that's a subject of another talk, they make a lot of the heavy elements, and then also some of the low mass stars, which are reaching the end of their lives, they can also make some of these heavy elements through other means. So actually, elements up to about iron or nickel or copper are pretty common, and as you go higher and higher up the periodic table, the elements get rarer and rarer and rarer, which is why gold is not very common in the universe, or uranium. So, we made all these molecules, good. How do we make, or we made all these atoms, good. How do we make molecules? They need a little help. And so remember that carbon sticks together and makes dust grains. They might be 1 micron, 1/1,000,000th of a meter in diameter. But that's still pretty big compared to an atom. And a hydrogen can come along, and hydrogen makes bonds with carbon, and a hydrogen atom can stick to a dust grain. Normally, hydrogen is a gas, and it's just floating out in space, but it's held there. Then another hydrogen can come along, and then from what are called van der Waals forces, these are random forces from the vibrations of atoms, these two hydrogens might migrate by chance close to each other, and then they form a bond between them, and then they float off into space, and finally, you have a hydrogen molecule instead of a hydrogen atom. And so that's where some molecules come from. You can also do this with oxygen, and you can do it with other elements as well. How do we observe molecules? They have molecular bonds which are pretty low energy and weak, and they can vibrate, they can rotate, and so the energies associated with molecules are very low, and those translate into long wavelength light. That would be millimeter waves, infrared waves, radio waves. And I should have put something in here. There's a very famous and powerful millimeter telescope in Mexico, which I encourage you to see, not too far from Puebla. And so we use radio telescopes and millimeter telescopes and submillimeter telescopes, microwave telescopes, to look for molecules in space, and also infrared telescopes. So this is an infrared telescope that was in orbit for a good many years, called Spitzer. So we have, in the space between the stars, we have dust that comes from red giant stars, and we have molecules. Now, dust is good and bad for astronomers. It's interesting physically. That's good. But it also blocks optical light. So if you look with a telescope and you see a cloud of dust, you'll see nothing beyond it. And it'll look like this. This region has stars behind it, but we can't see them because of dust. If you look in infrared light, the infrared light will actually penetrate through the dust. And that's why we use infrared waves and also radio waves to explore dusty areas of the universe. And if you look in long enough wavelengths, the dust will actually glow, because longer wavelength light corresponds to cooler things. And the dust is relatively cool. It might be 100, 200, 300 Kelvin. Your body temperature is about 300 Kelvin. You might think you're warm, but in the universe, compared to a star, you're pretty cool. This is why, double entendre, this is why actually we use infrared cameras to look for people, because you glow in infrared light. Has anybody looked through an infrared camera? Or seen the night vision goggles? Yeah, so astronomers use the same thing to look for dust, which is about at body temperature or even below. So we have these molecules in space. They're formed by catalyzing their formation on dust. So the dust helps the atoms to come together. But I want to emphasize that when we have clouds of gas and dust in space, they're lower density than the air in this room. Billions of times less dense. We can see them because they're big, but they're almost a perfect vacuum compared to what we can make on Earth. Also, a lot of them are very cold. 10 to 40 Kelvin, that's near absolute zero. So there was a very famous documentary called Star Trek: The Wrath of Khan. Has anybody seen Star Trek: The Wrath of Khan? With a very famous Mexican actor named Ricardo Montalban, who is one of the most famous actors that I've seen. So he said space is cold, very cold, and he's right. So if you watch science fiction, you will learn important scientific concepts. Just watch the right science fiction, Star Trek. So we have these cold clouds of gas and dust, but they're big. They're 100, 200 light years across, and that's why we can see them. And in our galaxy, we know of thousands of these, and they have masses 1 million times that of our sun. But remember, they're very big. Very, very big. That's why. And they form, and then they dissipate. And they form, and they dissipate. Just like on Earth and our atmosphere, we have clouds, and they form and dissipate as well. We have clouds of gas and dust in our galaxy. Now, these clouds of gas and dust will get little dense regions inside of them. Just like an Earth cloud has droplets that form around a dust grain, gas clouds in space have concentrations that actually also form. They're associated with clouds of dust. And that's where stars eventually form. Our galaxy makes about 1 star per year, 1 star about the mass of our sun. But our galaxy's been around for 10 billion years, and it made more stars in the past. So we're still forming stars in places like this. So here is the constellation of Orion seen through infrared eyes. So here are the normal stars. Here is the Belt and the Sword and Betelgeuse and Rigel and so on. And then this area is the same direction as one of our spiral arms with clouds of gas and dust about 1,500 light years away, something like that. And if you look with infrared eyes, you see them, and then these concentrated areas are where the stars are forming. And these clouds of gas and dust are giving off radio waves because the molecules in them, or even the hydrogen atoms, have very low energy transitions. And so radio telescopes help us to map out where the dust and gas are. I showed you how a hydrogen molecule forms. That's a simple one. That's 2 hydrogen atoms. We can get things that are much, much more complicated than this. Carbon dioxide has 3 atoms, carbon and 2 oxygens, okay? Water is oxygen, 2 hydrogens. That's also a pretty simple atom. They're very common, by the way. Ammonia is very common, formaldehyde. Now remember, the most common elements in the universe are hydrogen, number 1, helium, number 2, but helium doesn't bond with anything. It's a noble gas. And then after that, carbon, nitrogen, and oxygen are the next most common things. You have carbon with oxygen, water is oxygen with hydrogen, ammonia is nitrogen with hydrogen, formaldehyde is carbon, hydrogen, oxygen. They're all using the same combinations of a few elements. And then we have more common ones, like methanol and ethanol. We can have sugars. Amino acids, which are the building blocks of life, are mostly carbon, hydrogen, oxygen, and nitrogen. And we actually find one of the amino acids, a simple one called glycine, in space. But we can get even bigger ones. There are basically soccer ball type molecules of carbon called buckyballs. So once the molecules start to form in these cool, dense clouds of gas and dust, they get bigger and bigger and bigger. So some of the ones that we see, again, amino acid glycine, ethanol, which you probably see ethanol every day in some form or another. Buckyballs, yes, I was a student too. And so I have a couple of videos here, which I will cross my fingers that they nope. Yuda. That one. This is why I like Max. Okay. All right. Qué bueno. Oh, we need sound.
Most of them are simple molecules with 2 or 3 atoms. However, some of them are complex, and they include organic materials that have made people very interested in the possibilities of life in deep interstellar space. For example, the amino acid glycine, NH2CH2COOH, has been found, and acetone, CH3CH3CO, and ethyl alcohol, CH3CH2OH. Astronomer Ben Zuckerman calculated that the Sagittarius B2 molecular cloud, if cleared of impurities, would yield 10 to the power 28/5 of pure alcohol at 200 proof. However, the density of interstellar space is very low. A businessman once calculated that a 1 kilometer wide funnel being dragged at 10 times smaller than the velocity of light would take 1,000 years to fill a single shot glass of the alcohol that exists in space. The molecules in space are important because they show that complexity can be derived from simple atomic collisions provided the density is sufficiently high.
Come with me.
Nutella combina con pan tostado y con sonrisas. Combina con bolillo y con cariño. Nutella combina con el desayuno y con...
We discovered buckyballs in space. Fullerenes, or Buckminster fullerenes as they're called in full, are in fact an entire class of molecules. Buckyballs are these microscopic particles made of carbon that are arranged in a very specific pattern of pentagons and hexagons, which gives them the shape of a soccer ball. Buckyballs are like soccer balls in the precise way that the carbon atoms make up a pattern of pentagons and hexagons. In that sense, the chemical structure of these buckyballs is exactly the same as a soccer ball. We can detect buckyballs in space through their vibrational motions. These buckyballs, they oscillate or vibrate in very different ways, and each way they vibrate corresponds to a very specific color of infrared light that they emit or absorb. So it's the first detection of an entire new class of molecules that we know on Earth, but that we didn't know for sure whether or not they existed in space. Buckyballs are now the largest known molecules in space, and we have discovered them using the Spitzer Space Telescope. Astronomers are excited about the discovery of buckyballs in space, first of all because it is something that we have been looking for about 25 years now. The main reason being that these buckyballs are amongst the most stable and most durable molecules that we know on Earth, so they're ideal candidates to survive the harsh conditions in the interstellar medium in deep space.
Gracias. All right, so we have all sorts of interesting molecules in space, up to these extremely complex carbon molecules called the buckyballs. And then we also have something called polycyclic aromatic hydrocarbons. And here are some pictures of them. You see, this is not very strong. These things up here, they have multiple rings, basically. And they get to be incredibly complicated with hundreds and hundreds of atoms. And these all come from the simple building blocks that we had from the Big Bang and from stars forming heavier elements. Now, where does star formation happen? It happens in these dense clouds of gas and dust. Remember, dark areas are not empty. They're full of dust, and that blocks the optical light. And just like a star, a gas cloud also has a balance between pressure from the outside, its gas pressure, and gravity from the inside. And like a terrestrial cloud, these gas clouds can fragment and form little dense areas, which eventually will shrink due to their own gravity and form stars. So we see these happening now. They're protostellar, protoplanetary disks. This hamburger-like thing, actually, this is not empty. This is dust. This is a dust disk, and then it's glowing in infrared light. These are infrared pictures for the most part. This is optical. This is optical. These are infrared. And it looks something like this. You see a dense area in here. You see a disk of gas and dust, and it's spiraling in. It's called an accretion disk. And the pressure inside gets high enough that some of the material gets squirted out the holes. It's the path of least resistance. It's the same idea as if you have a bathtub. You're pouring water into the bathtub, and you pour it too fast. What's going to happen? The drain cannot take it all, and some of it splashes back. So this is the splashback from the gas being dragged in by gravity into this central dense area. So we call them protostellar disks, also protoplanetary disks, because on the outside is where the planets form. These are actual pictures. This is from the Atacama Large Millimeter Array in Chile, and you can see a face-on disk with these regions with less dust. This is dust emission. This is in submillimeter light. So this is cool dust, and it gets warmer and warmer and warmer the closer you go to the middle. And we think that there are planets or protoplanets which are vacuuming up the dust and making these dark rings. Here's another one. We made a little eclipse here with an instrument because the starlight in the middle is too bright, and we can see a disk of dust and gas around this protostar. This is an infrared light. And this distance here is about 1.5 times the diameter of Pluto's orbit, or Neptune's orbit. So, cross your fingers that this works here. Have a little animation of how this looks. Hooray, it works. So we have a cloud of gas and dust. Gravity will it has a little bit of spin, just a teeny bit in some direction, and then it will collapse into a rotating disk first. In the middle, you'll get a forming star, protostar yet. It's not starting nuclear fusion. And in the outer edges, you have a disk where it's just mostly gas and dust. The gas will evaporate away. The dust is left, and the dust will collide and gravitationally grow and form planets, and you'll have a star with a number of planets going around in a disk in various orbits. That's how we think it happens, and we actually see this happening toward many young stars. So, the last chapter here, we've had how elements form, how you form molecules, where you form stars and planets. Life. Now, there's another documentary which you should see. It's called Young Frankenstein. Has anybody seen Young Frankenstein? It's about life. If you haven't seen it, this is another tarea. You need to watch this important science fiction to learn serious scientific concepts. So, life, it's life. What does life need? We think it needs liquid water. Why? There are a number of good reasons. Number one, water is really common in the universe. It's an oxygen atom with 2 hydrogens. Hydrogen's the most common element in the universe. Oxygen is something like number 3 or 4, something like that. So there's a lot of water in the universe. We have water in our solar system. Uranus and Neptune have a lot of water. Jupiter and Saturn have water. There are icy bodies like Europa and Titan, they have water as well. And Earth, of course, has water too. So it's very common. It's liquid over a pretty good temperature range for a reasonable pressure. And being liquid makes it a good solvent for chemical reactions to happen, complex chemical reactions. Also, it's thermally stable. It takes a long time to heat up and a long time to cool down. So it keeps the temperature stable. And also, it has a very interesting property which many materials don't have. It expands when it freezes. And so you can get a shell of solid material with liquid underneath. That doesn't happen with a block of iron or nickel or magnesium or some metals, for example. It doesn't happen with silicates, with sand. You have the solid stuff which is more dense than the liquid. But with water, the solid state is less dense, and so you have basically this insulation which on the top in the form of ice, which helps keep liquid water liquid. Also, it has a high surface tension, so it forms droplets and spheres. That's also quite important. Let's go back to, so we have lots of water in the universe, and then carbon. Carbon is very common. You've seen all of the carbon molecules that we have in the universe that we observe in space. Now, carbon has a very, very interesting property that it forms chains, and it has a lot of complexity and also flexibility too. The molecules are flexible, unlike silicon, which has a similar valence. Carbon has a valence of 4, so it can form bonds in 4 directions. Silicon can too, but the carbon bonds are flexible. Silicon bonds are not. Carbon also forms rings. So the complexity of molecules with carbon is enormous, and then it can also form bonds, of course, not only with itself, with hydrogen, with oxygen, nitrogen, and other atoms. So carbon makes an incredibly large number of atoms, and molecules, and they can be interchanged and converted rather easily when they're dissolved in water. So, let's look at our solar system. What do we have in our solar system? We have a number of bodies with a lot of water. One of them is comets. How many of you have seen a comet? Okay. There are comets every year, but they're faint. You have to look. But most years, there's at least one comet that can just barely be seen with the eye. The really spectacular ones are rare, unfortunately, and I hope you see them. Halley's Comet will come back in 2063. I hope you see something brighter than that in the next 5 to 10 years. Anyway, comets have a lot of ice in them, and what you basically have is it's like a piece of styrofoam, and it's darker than charcoal. It only reflects a few % of the light that hits it. Comets are the darkest bodies in our solar system. They're darker than a black piece of paper. And so they also have a lot of water, and what are called volatiles. These are molecules with low melting and low boiling points. And so when these bodies, they have very elliptical orbits, they come close to the sun, the low melting and low boiling point molecules evaporate away and form a cloud around these blobs, which are a few kilometers across. And you see the comet begin to glow, and then the solar wind and the sunlight push away this gas and dust, and it forms a tail. So comets are actually very beautiful, but they're also very interesting because they have a huge number of molecules in them, and they tend to come from the outer solar system where not much happens. They're a deep freeze sample, una muestra, from the early solar system. So here's a spectrum of Halley's Comet from its last approach in 1986. And we see all sorts of simple molecules. We see cyanide, we see carbon-2 and an ammonite and so on. So we have a lot of molecules in comets in the outer solar system. There's another one that was explored a few years ago, Churyumov-Gerasimenko. We call it 67P because it's a shorter name. And this is a short period comet, but the European Space Agency actually sent a space probe to this one to orbit it and land on it as well. So this is shaped like a rubber duck. This is a few kilometers across. Halley's Comet is about 16 kilometers across. It's shaped like a peanut. This one is more like 3 by 6 kilometers, something like that. It's very, very small. And it's made of stuff, so is Halley's Comet probably, that's very porous. So it's less dense than water if you could put it in water. It's like polystyrene. It's like styrofoam. But it has dirty styrofoam. It has carbon, it has oxygen, it has water, it has ammonia, it has amino acids in it as well. And if you were to land on a comet and jump, you would fly off into space because the gravity is so weak. That's why the gas also goes away from it. And so this is a close-up picture of the surface of this comet, and you see that it's got all of this fine structure and grains and so on. Here you see some jets of material coming out. Coming close to the sun. So comets are really interesting samples of what our solar system used to be like 5 billion years ago when we formed, with lots of molecules forming in the cold parts of the solar system. Now, when we look at our outer solar system, this would be Jupiter, Saturn, Uranus, and Neptune, we also see something else which is really strange. They have reddish surfaces. These are not the planets because they're balls of gas. But the moons around the planets, like Europa and like Titan, have reddish surfaces because they have complex molecules that we call tholins. So how do you get a tholin? A tholin is you take some organic molecules, you hit them with ultraviolet light, it breaks the bonds, and then they reform in complex ways. There's no simple formula. This is basically red gunk and red junk. So you have the molecules being destroyed by ultraviolet light and then reforming, making this red stuff. And we see many red bodies in the outer solar system with organic molecules. Here's one, Titan. Now, Titan is very interesting. It's a satellite of Saturn. It's on the order of the size of Mercury, maybe even a bit bigger. And it has an atmosphere as well. It's very cold. So because it's cold, it can keep its atmosphere. The molecules are not moving too fast. This is an infrared picture. So Titan actually is very interesting because it's too cold to have liquid water. The ice there is frozen. It's very hard. It's hard like steel. But there are other molecules which act like water. Ethane, for example. Ethane in Titan is in the atmosphere, and it's in lakes. It has liquid ethane, and it has solid ethane. There's a cycle, just like we have rain and snow and liquid water and clouds. Titan has ethane rain and ethane evaporation and ethane ice. Now, the temperature is a bit too low for life to be there, we think, but it is a parallel system to what we have on Earth. And again, it's a deep freeze sample of the organic molecules, the complex molecules that existed in our solar system from the beginning about 4.5 billion years ago. And just to let you know how cold it is, it's colder than Antarctica on the coldest day. It's 180 below Celsius. The surface, like I said, has lakes and rivers and so on. Here's a picture from the surface of Titan. And it's a bit like a creme brulee. It has a crust and then it has a soft underneath. And we think that it may have a liquid water ocean underneath, which would be heated up by some unknown mechanism. It could be tides from Saturn, or it could be maybe some radioactive decay. I'd like to try again, little animation, because this is pretty neat, because the European Space Agency, landed on Titan. This is the probe coming in, and it had a microphone. We could record, I think it recorded the real sound going through the atmosphere. that's what we got. Now, it lasted for an hour or two. That was it. But I hope in our lifetime we go back to Titan because it's a really interesting place. Okay, Europa is a satellite of Jupiter. Look at this red stuff. Remember, Titan was a bit orange from tholins. Europa has an icy surface, and it has this red stuff, tholins, organic molecules in the cracks. And if we look up close, we see lots of red stuff in the cracks. We think the ice is anywhere from 10 to 50 kilometers thick, and underneath that is liquid water. Now, the heat source here is tides from Jupiter. Jupiter is twisting and flexing Europa in its orbit. It's like taking a wire and bending it and heating it up. And so this ocean of liquid water has a heat source from underneath. It's protected, it's insulated from space by this icy layer. There's red stuff, there are organic molecules here, and we see that this ice breaks up occasionally. There's a meteorite impact, it'll break the ice, mix the material, and then it will refreeze in space. And so we actually see material coming out of Europa in the form of geysers. And there's a mission.
NASA's Hubble Space Telescope has directly imaged what may be plumes of water vapor on Jupiter's icy moon, Europa. Europa has long been thought to harbor a global ocean of water beneath its surface of ice, making it a prime target of study for anyone interested in searching for alien life. Eventually, our search for life will take us into that ocean, but until then, the existence of a water vapor plume would provide an early glimpse into the ocean's conditions. In 2012, a team of astronomers used the Hubble Space Telescope to observe a faint aurora from the interaction of Europa and Jupiter's magnetic field. They detected emissions in wavelengths characteristic of the breakup of water molecules, and after considering a wide variety of causes, the team concluded that the most plausible explanation for these spectroscopic measurements was the existence of plumes of water vapor erupting from the surface of Europa. Now, a different team of astronomers has used a different method with similar results. They used Hubble to image Europa in ultraviolet light as the moon transited across the disk of Jupiter, and were actually able to take direct images of what appear to be the silhouettes of plumes rising about 125 miles above the surface of Europa. If these observations are indeed of water vapor plumes, then they approximately match the 2012 observation estimates for the plume's mass, height, and location. Also, these plumes are transient, meaning they come and they go. Out of 10 observations of Europa transiting across Jupiter, the team saw possible plumes on just 3 of the transits. Both the recent observations and the 2012 observations provide evidence, not proof, of water vapor plumes on Europa. Science is a process, it's not always cut and dried. But future observations by Hubble and infrared observations by the James Webb Space Telescope could continue to build a case for the existence of these plumes on Europa. And then NASA's future Europa flyby mission would continue the search for the plumes and visit them to look for evidence of a habitable underwater world.
So Europa is where it's at, and we have a probe going there now. The European Space Agency built something called the Jupiter Icy Moons Orbiter, the JUICE mission. It's on its way. There's another one being built by NASA. It's called the Europa Clipper, and that's going to be launched soon. And both of them want to explore this small world. It's about the size of our moon, actually, but it has incredible complexity, and we would like to know what's going on inside of it. Because of all the places in the solar system, this is one of the best places to look for life outside of Earth. Okay, another place which has tholins. You would never expect it. Pluto. This is satellite Charon. And then this is a small body a little bit outside of the orbit of Pluto called Arrokoth. It used to be called Ultima Thule. And this is red because it has these complex molecules, tholins, organic molecules which were dissociated by ultraviolet light and then reformed in much more complex ways. This one too, this is a few kilometers across. And this is 2 bodies that stuck together. Looks like a snowman. So these molecules are all over the place in our outer solar system. It's amazing. We didn't imagine it. And actually, what's frustrating is the way to find out what these molecules are, you have to put them through a mass spectrometer. You either have to put a laboratory up there or bring them to Earth. We won't bring them back to Earth, but to send probes out there takes years to get out there. I hope again in our lifetimes that we will go back and visit and maybe even land on Pluto and try to sample some of this red material. Now, what about Earth? There is life on Earth. Last I looked, I hope so. Now, the problem is we have an oxygen atmosphere, and oxygen will break down these tholin molecules. However, oxygen is a relatively recent addition to Earth. The original Earth did not have an oxygen atmosphere. Far from it. Actually, oxygen is reactive. If we didn't have plants replacing the oxygen in our atmosphere, the oxygen would eventually bind with rocks and so on, and so the oxygen will go away. The mere fact that we have oxygen in our atmosphere means that we have life which is generating it, because it's not stable. And oxygen appeared about 2.5 billion years ago with the appearance of what are called cyanobacteria, which take sunlight and carbon, and then they metabolize it and give off oxygen. They're basically the first plants. So, did we have tholins in the past? Well, there was an experiment back in the 1950s called the Miller-Urey experiment, where simple molecules, this would be carbon dioxide, water, and ammonia, were sparked in a chamber. And then after some time, complex molecules arose, including over 20 amino acids from water, ammonia, and methane, probably carbon dioxide as well. So we probably had these in our early atmosphere. Remember, no oxygen at the time. But the problem is, in the very early history of Earth, it was not a very nice place. Earth was hot. It was formed by bodies hitting each other. And so the surface was molten. That would be 1,000 to 1,500 Celsius at a minimum. That's enough to melt rock. We live on a sand heap. Ricardo Montalban, as Khan Noonien Singh, said that he lived on a sand heap. Well, we do too. The Earth is largely made of silicates, sand, that's our mantle. And when you heat up silicates, you get liquid rock and lava. And this is what our early Earth looked like. It was not nice. No liquid water, it's too hot for that. And probably not much of an atmosphere yet. It developed an atmosphere from light elements and molecules coming out. It's called outgassing, nitrogen, carbon dioxide, things like that. So where did the water come from, and where did the molecules come from? We think that they came from the outer solar system. The form of asteroids for the water, because our deuterium content is like that of asteroids. And then all of those places you saw that were red in the outer solar system, if a chunk of them breaks off and comes here, they will give us complex molecules. It'll have to happen after this stage, and it'll have to happen after we get water for interesting things to happen. And remember, there was no oxygen back then, so the tholins could stay. Now, in the early Earth, about 3 billion years ago, we had water, we had some carbon dioxide, methane probably not so much, but we also had about the right temperature for liquid water. We had organic molecules coming in, and so we had water as a solvent, we had molecules, complex organic molecules, and we had all the ingredients for complex chemistry to evolve. Now, how did life arise? This is the big question, la gran pregunta. We're still working on that, but remember, water has a surface tension, and it forms globules, and then some of the complex molecules can form layers that envelop these droplets. So that's some of it. But between 3.4 and 3.7 billion years ago, we have rocks called stromatolites. Stromatolites are fossils from layers of bacteria, bacterial mats, and they grow like this. They get piled up higher and higher and higher. This is from Australia, and so we have evidence of bacteria from very close to the solidification of Earth. The solar system's a little over 4 billion years old. The Earth solidified probably around 3.9 billion years ago. The moon formed then too from a giant collision. Soon after that, we had life. So life formed early, and we had all the ingredients. And it all comes back to the formation of molecules from the first elements. So that's where I'm going to leave it here, and it's up to you to figure out how we got life I'll be happy to take questions.
Thank you very much, Jerry, for your very good and very interesting presentation. So, have you got any question? It's important to use the microphone if you want to do a question, to ask. Okay.
Thank you. So at which point does the fusion start to occur when the star is actually beginning its new process?
Okay, that's a good question. In the disk of material, gravity is pulling in, and material from the disk will fall onto the star. Now, there's a law of physics that says the more you compress something, the more you heat it up. It comes from the same concept that if you hit something with a hammer, it heats up. If you pump air into a tire, it heats up. So when the middle of that object, which we call a protostar, reaches 6 million Kelvin, that's the minimum temperature you need for hydrogen atoms, or hydrogen nuclei, for protons to stick together and start fusion. So it starts at the temperature of 6 million Kelvin. Our sun is about 15 million Kelvin. So it's a bit bigger, it has more mass, more gravity, and so it can hold a higher temperature inside. But that's the threshold. There are some objects that don't reach 6 million Kelvin. We call them brown dwarfs. They don't start fusion. Brown dwarfs. I want you to think about molecules tonight after this talk. Think about some of the molecules you saw in this talk as you go out and do whatever you're doing.
So I got a question.
Water.
Hello.
Yes.
So are tholins and life incompatible?
Well, tholins are complex molecules. We actually only have a rough idea what they are because they're so complex we would need a mass spectrometer to analyze them. We know roughly what they're made of, but we don't know exactly what their forms are. They're complex molecules, though. Complex organic molecules with carbon, hydrogen, oxygen, nitrogen, and other things.
Another question? Okay.
You mentioned that most of the elements, well, the light elements were formed at the core of the stars.
Right.
But what about all the other elements?
Ah, okay.
Aside from the ones that you said that originated from the fusion of two neutron stars?
Oh, well, some of them are formed in nuclear fusion. That would be the even-numbered ones. So that, for example, whoops, not showing anymore. Huh, okay. All right. Even-numbered elements form in stars. So this would be helium. You skip over beryllium because that doesn't have a stable nucleus, really. Carbon, oxygen, neon, magnesium, and so on. You build it up to iron. And when the star explodes, there are what are called endothermic reactions. So the elements up to iron form because they give off energy as they're forming and they keep the star going. When the star explodes, then it can make other elements which are not energetically favorable. They absorb energy as they're made. But that's how you get copper and so on. Now, the very heavy elements form when two neutron stars merge. Those are the remnants of the supernovae. And you can form things like gold and platinum and so on. So they do form. There are different pathways. I had the slide up here. There are actually a number of different ways that elements form. The rare ones form in less common situations, but they exist.
Okay, thank you.
So my question is, so we see pictures about like the video that you showed us that was like the robot arriving to different planets or different moons. How do you identify what type of molecules there are from just photographs or, well, not like any physical interaction, only just pictures or a thermal analysis? How do you do that?
Brilliant question. Okay, astronomy is the science of look but don't touch. We have been to the moon. 12 astronauts went to the moon, and they walked around in the soil. We've landed robots on Mars. We've landed on a comet, and a couple of asteroids, not necessarily as primary mission. We landed on Titan. That's it. Now, we use light, as Dr. Graney said, we use light and spectroscopy to analyze what elements and what molecules and what temperatures and what densities are in something. Spectroscopy can tell you a lot. We can tell you the density and the temperature and the element abundances in the atmosphere of our sun with great precision by using basically atomic physics, the excitation and de-excitation of electrons and the light that comes in and goes out of atoms. Molecules do the same thing. So spectroscopy will tell us a lot. The trouble is, with elements, we can tell most of the time what an element is and an ion, and you strip off a few electrons, then the spectrum looks a little bit different. The lines, the pattern of light coming out and light going in changes. With molecules, there are so many possible transitions. With complicated molecules, it gets very hard to identify what molecule makes what feature in a spectrum with emission and absorption of certain wavelengths of light. So that's where it gets tough, and that's when you need to land a laboratory someplace, take a sample of something, basically burn it, and then figure out what the weights are of the various atoms inside.
Okay, thank you.
Another question? Have you got another question? There's one. Oh.
Hi. You say that the protons and neutrons made the hydrogen, right?
Well, you make iron by slamming helium atoms into lighter things.
Okay.
So things like titanium.
And what about the electrons?
Okay, the electrons are
also in
the middle of a star. The electrons are stripped off. So you have what's called a plasma. A plasma is a gas where you have the nuclei of atoms and the electrons floating freely. The electrons are not attached. And so sometimes the nuclei can slam together. In the outer parts of a star, it gets cooler and cooler, and you'll find some atoms that have electrons attached. The electrons are always there. It just depends on whether they're attached to the nuclei or not. For fusion, it's so hot, the electrons are just there. They don't offer much resistance to the nuclei. What they will do is a photon will bounce off an electron much more easily than it'll bounce off of a nucleus, and that has to do with basically quantum mechanics.
Another question is, how do you know how old is a molecule?
We use spectroscopy. We can identify the transitions of electrons for simple molecules, water, ammonia, ethanol, things like that. Glycine we can figure out too. If we can make it in the lab and we can analyze how light shines through it, we can determine what wavelengths of light get absorbed, what wavelengths of light get emitted, and compare it to what we see when we pass light from a star, light from a nebula through a prism or a grating, and then say, okay, that's what we have in the lab. That thing is glycine. That's sugar. That's sucrose. But we have to make the molecule here first and analyze what wavelengths of light it absorbs and emits. If we see something we can't identify, we might spend a long time trying to figure out what duplicates it in the lab. That's why the complex molecules are tough to identify.
Thank you.
Another one? No, that's okay.
So you said there might have been tholins on Earth before oxygen formed in the atmosphere. Do you think there could be still traces or tholins, let's say, in the lower layers of the Earth or frozen in Antarctica, or they're long gone?
Antarctica has been heated up and cooled off a lot. Tholins get destroyed by oxygen and by heat. So I don't think there's anything left. However, we probably can find good substitutes. That's why I say comets are a deep freeze sample from the early solar system. If we go to bodies that haven't changed, Earth has had continental drift, it's had pieces of its crust shoved under other pieces of its crust, it's had volcanoes erupt, it has oxygen breaking things down. I don't think anything survived here. We've changed a lot. But the objects in the outer solar system are cold and have not changed. And we can find what was here out there now.
Well, I think it's time we went. No?
Okay. I would like to show, by the way, we have the University of Louisville people also make t-shirts. So this was from the 2017 eclipse. The greatest 2 minutes in astronomy. It's because the Kentucky Derby is the greatest 2 minutes in sports. It's a 2-minute race. And so I encourage you, I'm going to be talking about the eclipse, go to the eclipse in April. Go to the eclipse in April.
Why don't you tell them about the tomorrow? No,
tomorrow I talk about quasars.
Yeah.
Quasars and black holes, giant vacuum cleaners in space that bend the laws of physics and bend space-time. And then on Thursday, I'll talk to you about eclipses. It will be complementary to what you saw yesterday.
Okay. Thank you. Please, can we give us an applause? Thank you.
Placer es mío.
Y en el nombre del Departamento de Matemáticas y Física de la Dirección General Académica, queremos, we want to give you a certificate and a little present. Thank you very much for your interesting talk,
okay.
Your lecture.
Okay.
Thank you, and gift from the Dirección General Académica. Thank you very much. Applause. Thank you. Thank you. I hope you enjoy.
Gracias.
Jóvenes, los esperamos mañana. Ojalá y nos puedan acompañar. Gracias a todos los que se quedaron aquí. Ojalá les haya gustado y esto motive el estudio de la astronomía. La intención es eso, que lo consigan.
Tarea. Watch Star Trek. Watch Young Frankenstein. Tonight, think about some of the molecules you saw in this talk, like water. And discuss them.
Los esperamos mañana, jóvenes. Ojalá y nos acompañen mañana los siguientes días, miércoles, jueves y viernes. Gracias, gracias a todos.